So finally, there's a few other trends that we're going to be able to get as basic information from the periodic table. And these include such things as how large an atom is, how easy it is to remove an electron, what we call ionization energy, as well as how much an atom wants more electrons, or electron affinity. So these are all things that have some very easily predictable trends from looking at the way the periodic table is set up. So let's start with atomic size. I'm not going to bring up the actual periodic table, just going to think of it in this way. And the reason we can make a lot of these trends is because of these patterns that we see with the way the electrons are configured. Elements in the same group, the same column, have similar electron configurations. So if you look, for example, at our periodic table, and you look at nitrogen, nitrogen is 2p3 is how it ends. Below it is phosphorus, 3p3, arsenic, 4p3, 5p3 for antimony, and so on. And that same thing is true for every column on the periodic table. So how is size influenced? Well, as we go down the periodic table, we end up at higher energy levels. And so the outer electrons are further from the nucleus. And so in general, as we move down the periodic table, we end up with larger atoms. And we can see some examples of that on this chart. So let's bring this chart in. This chart, as you can see, is atomic radii placed within the periodic table. And so if you look right down group 1, you can see as we go from hydrogen to lithium, that's 1s versus 2s, to sodium is 3s. The radii, which are all listed in picometers, are generally going up. Now, what happens as we go left to right? And if you look right across the second row here, (128), (96), (84), (76), (71), (66), (57), and then 58 for neon. What's happening there? Well, with the exception of neon, as we're going from across the periodic table, the number of protons increases. But this is at the same energy level. So when it comes to size, we have more protons pulling on those electrons as we go to the right, without going to a higher energy level. And so because of that, the atoms on the right side are smaller than those on the left side. So the size of an atom increases going to the left and increases going down. So where do we find our largest elements? Well, in general, they're going to be down at the bottom left. And specifically, if you look at all of the radii that we have listed here, where do we find the one with the largest radius? Right at the bottom left, and that being francium. All right, what else can we predict? We can predict ionization energy. And by predict, I don't mean we can predict actual numbers, but we can predict trends. And in a lot of cases, while exact numbers would be great to have, the trends end up being the most important thing that we have. Because the trends are something that we can recognize and remember fairly easily. So let's look at a chart. Take a few seconds and look at this and think about what are the general trends that you see on this chart. So this one, the trends, some of them are as obvious as they were for size, but some of them are a little less obvious. So what's the obvious one? The obvious one is that hopefully you see, as we go down the periodic table, the ionization energy also decreases. But before we get too into that, let's make sure we have a good definition of ionization energy. So ionization energy is the energy that is required to remove an electron while an element is in the gas phase. So let's think about if what we're seeing here makes sense. As we go down the periodic table, we're starting to have our valence electrons be farther and farther and farther away from the nucleus. And so as those electrons get further away from the nucleus, the protons are not able to hold on to them as much. And so that should make sense to us. Now what happens as we go across the periodic table? Now there is one overall trend. You can see we start over here in our second row at 520 and we end at close to 2100. So clearly it is increasing as we go across the row, but not everywhere. So notice as we go from beryllium to boron, it goes down. And the same thing happens between nitrogen and oxygen. So in other words, we go from lithium up to beryllium, back down slightly to boron, Then we go up to carbon, and up again to nitrogen, back down slightly to oxygen, and then up to fluorine, and up again to neon. So why that type of trend? Well, this has to do with stability. Filled orbitals are generally the most stable. But half-filled orbitals also have some extra stability. So if we go back to our periodic table, we have lithium. Pretty easy to take an electron away. Another reason, and we'll get to these things later, or actually let's talk about this now. Noble gas configurations are the most stable. So if we look at lithium, or any of the group 1 alkali metals, if they lose an electron, they end up in a very, very stable configuration, that of a noble gas. And that's also seen by the noble gases. If we look at how high their ionization energies are, we can see it's very difficult to take an electron away from those. So we go from lithium to beryllium, the ionization goes up. Because when we're in group 2, we have a filled s orbital. Whereas when we get to group 13, this is a p1. So in fact, losing an electron from group 13 takes us back to a stable configuration where the s orbital is filled. We go from boron to carbon. We get, again, more protons, so harder to remove. Same thing to nitrogen. But nitrogen, or group 15, these are p3 elements, which means we have a half-filled p orbital. So that's a little bit more stable than group 16. So that's why group 16 actually has a slightly lower ionization energy than group 15. And then from there, we go up and we reach our max at the noble gases. All right, what about electron affinity? So electron affinity is the opposite of ionization energy. This is the energy change from gaining an electron. Now, what would you expect to find here? So would you expect something opposite of ionization energy? So an element that, so in other words, an element that wanted to give up electrons is probably an element that doesn't want to gain them. And so let's bring up the actual numbers and see if that's true. So here's an electron affinity table. And so if the opposite is true, what you would expect to see is that electron affinity would go down, because as we get further away from the nucleus, there's less attraction for electrons. And that's the exact trend we would see. As well as we would expect it to, in general, increase going to the right. Because those atoms want to gain electrons. And again, we see a little bit of this same type of trend in here based on the half-filled orbitals. But basically, that's exactly what we find. Electron affinity is the exact opposite trend from ionization energy, with one major exception. And that's the noble gases. Notice the noble gases, not only do they not follow the trend, but for the noble gas, it actually costs energy to gain an electron. Why is that? Well, the noble gases already have a filled shell. They don't want any more electrons. And so it's actually very, very difficult to get a noble gas to add an electron. So that is it for chapter 8 at this point. And we will start shortly into that's the end of chapter 7. So shortly after this, we will start into chapter 8, where we start talking about bonding as well as geometry and the shapes of molecules.